Hi, my name is Terry Zhang. I'm a PhD student at Human Development Department. Today, I'll talk about this project on estimating propensity score with multi-level observational data. This is a joint work with my advisor, Professor Brian Keller. To start, by definition, propensity score is the probability of receiving a treatment given covariates. Propensity score is widely used in observational studies where the goal is to use propensity score to reinstall the balance between the treated group and the control group. Once such covariate balance is established, then an unbiased causal effect can be estimated. That being said, propensity score can also be used in randomized control trial, for example, for re-randomization purpose. Okay. Previously, the propensity score is usually estimated with using logistic regression for single-level data. For a multi-level data, for example, students nested within class, nested within schools, multi-level random effect or fixed effect model can be used. However, these parametric methods all have their assumptions. In the past decade, machine learning methods has been shown can outperform logistic regression in certain settings. However, these studies are all focused on single-level data, where they assume data are coming from a identically and independently sampled distribution. Therefore, the goal for this study is to further examine the performance of leading machine learning methods to estimate propensity score in a multi-level observational setting as compared with more traditional parametric methods. Okay, to study this topic, I conducted a Monte Carlo simulation studies. For the sake of simplicity, I only have one school level covariate Wj and one student level covariate Xij. For Xij, I have a random slope component to represent different effects to the treatment across clusters. Following previous literatures, I keep certain factors constant, and I manipulated 4 factors. The interclass correlation, which is an indicator of the degree of multi-level structure. The number of clusters, or in other words, number of schools. Cluster size represents how many students per school, and also the degree of nonlinearity, which is represented here as a squared term. The performance are measured by 2 matrices. First of all, the model convergence rate is defined as the number of converged model divided by the total number of replications, which is set to 500 in this case. In terms of model accuracy, I used root mean squared prediction error. Okay, let's take a look at the results first. In terms of convergence rate, on the left chart here, you see that both random intercept model and the random slope model have model convergence rate, especially when the interclass correlation is low at 0.04. On the other hand, the single level logistic regression and machine learning method in this case, GBM, does not have model convergence issue, providing good alternatives. In terms of cluster size and the number of clusters, we see that all models require a certain number of samples within each cluster and a number of clusters. Otherwise, you will run into a model convergence issue. Now, notice that here we only have 2 covariates, where in reality, we often have more than 2 covariates. Therefore, the model convergence issue for multi-level linear methods will likely to exacerbate. Lastly, in terms of model performance accuracy, we see that in linear methods, machine learning methods perform about the same with multi-level linear methods. As ICC goes up, single level logistic regression perform the worst among all methods, which is as expected. On the contrary, for the nonlinear cases, we see that machine learning methods is outperforming all linear multi-level linear methods, providing good choices for model accuracy. So in summary, the takeaway of this lightning talks are: A, propensity score methods are very useful in estimating causal effects. 2, using ordinary multi-level linear methods may run into convergence problem. And 3, researchers should consider use machine learning methods as good alternative. Now, finally, for future steps, I haven't shown you how to use machine learning estimated propensity scores to reinstall balance of covariance and ultimately reduce balance of treatment effect, which is a work in progress. Thank you.